Hello everyone, I am the lecturer, Wang Shengda. In this lesson, we will study the concepts of crystallinity and crystallization rate. Through this lesson, you will understand the concept of crystallinity and its measurement methods, the concept of crystallization rate and the factors influencing it, be able to identify methods for determining polymer crystallinity, and develop scientific thinking and a rigorous working attitude. Crystalline polymers always contain both crystalline regions and amorphous regions. To describe this quantitatively, the concept of crystallinity is introduced. Crystallinity is expressed as a percentage by weight or by volume. Crystallinity refers to the mass or volume percentage of the crystalline portion in a polymer material. The calculation formulas are as follows. Mass crystallinity equals the mass of the crystalline portion divided by the total mass. Volume crystallinity equals the volume of the crystalline portion divided by the total volume. It should be noted that the boundary between the crystalline and amorphous regions in polymers is not clearly defined, making it impossible to precisely determine the amount of crystalline material. Therefore, the concept of polymer crystallinity lacks a precise physical meaning. This is because different measurement methods correspond to different degrees of structural order. Or in other words, each method defines crystalline and amorphous regions differently, resulting in varying crystallinity values depending on the method used. Sometimes, the differences can be quite significant. Hence, when reporting the crystallinity of a polymer, the measurement method must be specified. Common methods for measuring crystallinity include density method. The measured value is called density crystallinity. X-ray diffraction method. The measured value is called X-ray diffraction crystallinity. Differential scanning calorimetry. The measured value is called DSC crystallinity. Infrared spectroscopy. The measured value is called infrared crystallinity. The density method is the most commonly used and simplest method for determining polymer crystallinity. It requires the following data: crystalline region density calculated from crystal's structure parameters, amorphous region density extrapolated from specific volume temperature curves of the melt, and sample density measured using a density gradient column. The density crystallinity is then calculated using the following formula. The crystallization rate is a fundamental physical quantity in the study of crystallization processes, and a primary focus of crystallization kinetics. The definition of crystallization rate varies depending on the measurement method. The crystallization process consists of nucleation and growth. Nucleation can be classified as homogeneous nucleation or heterogeneous nucleation. In homogeneous nucleation, ordered chain bundles form within the polymer melt due to thermal motion, serving as crystal nuclei. In heterogeneous nucleation, residual crystalline polymers, foreign impurities, dispersed solid particles, or the container walls act as senders, where polymer chains adsorb and arrange orderly to form crystal nuclei. Homogeneous nucleation occurs at lower temperatures. Heterogeneous nucleation occurs at higher temperatures. The crystallization rate can be measured by observing, at a constant temperature, properties related to the overall change in the sample's crystallinity, that is, the overall crystallization rate of the specimen. For example, one may measure how specific volume changes over time using methods such as dilatometry, optical depolarization, or differential scanning calorimetry (DSC). Or directly observe the change in spherulite radius over time under a polarizing microscope using hot stage polarizing microscopy, small angle laser scattering, SALS. The factors affecting crystallization rate are the same as those affecting crystallizability. The first factor is the molecular chain structure. The simpler the chain structure, the higher the symmetry, the better the stereoregularity of the chain, the smaller the steric hindrance of the substituent groups, and the greater the chain flexibility, the faster the crystallization rate will be. For instance, polyethylene has a simple, symmetrical, and regular structure and therefore crystallizes extremely rapidly, even when quenched in liquid air at 190 degrees Celsius. Polyethylene cannot form a completely amorphous sample. The lower the degree of branching and the higher the isotacticity, the faster the crystallization rate. The second factor is molecular weight. For the same polymer, under identical conditions, a lower molecular weight results in a faster crystallization rate. Since crystallization depends on the mobility of polymer chains, higher molecular weight leads to slower crystallization. The third factor is stress. Stress affects the crystalline morphology. When the melt crystallizes without stress, spherulites are formed. Under stress, extended chain crystals, shish, kebab, or columnar crystals may form. Stress also influences crystallization rate, as it can orient molecular chains along the direction of the applied force, thereby increasing the crystallization rate. The fourth factor is impurities. The effect of impurities is complex. Some may hinder crystallization, while others may promote it. Substances that promote crystallization often act as nucleating agents during the crystallization process and are referred to as nucleating agents. The final factor is temperature. Temperature has a profound influence on crystallization rate. Even a slight temperature difference can cause the crystallization rate to vary dramatically, sometimes by hundreds or even thousands of times. In this lesson, we have learned the concept and measurement methods of crystallinity, as well as the concept of crystallization rate and the factors that influence it.